All right, so today we're diving into a mission that sounds like something straight out of science fiction. Hitting a single spot on the moon with three different lasers, all fired at the same time from Los Angeles. We're going to break down the absolutely mind-bending numbers and physics involved here, from the scale of time and distance to the insane precision you'd need to pull this off. This is really the core of the problem, right? You're not just pointing a laser pointer at the ceiling. We're talking about hitting a moving target 250,000 miles away, and you have to account for, well, everything. The Earth's rotation, the moon's orbit, even the speed of light itself. It's an incredible cosmic puzzle. Every mission to space has to start on the ground. And for us, it all begins with three specific points in Los Angeles that form what we're calling the LA Triangle. These are our launch pads for this whole operation. Now look at this. These distances are, well, they're nothing really. Just a few miles separating each location. But this little triangle on the ground is the absolutely critical baseline for a calculation that's going to stretch across 250,000 miles of empty space. It's the base of a ridiculously long and skinny triangle that points all the way to the moon. Okay, so the lasers fire. And this is where the scale just completely shifts. We're not talking about miles anymore. Now we're in a race that's judged by the speed of light, where the difference between first and second place is measured in billionths of a second. So here's a crucial detail. This race isn't on a flat track. The laser from the Hollywood sign has a literal head start because it's higher up. It has just a little bit less distance to travel to reach the moon. But you have to be asking, how much difference can, 1,400 feet really make in a race this long? Well, that much. Just 1.43 nanoseconds. That's the winning margin. The Hollywood sign beam gets there first by a time so small it's almost meaningless to us. It's about the time it takes light to travel 1.5 feet. It's an almost impossibly close finish. And here are the official results of our photo finish. First place, just as we expected, goes to the highest point, the Hollywood sign. Griffith Observatory Knob second, and our starting point on Wilshire comes in third. It's just amazing that even at 186,000 miles per second, a little bit of elevation on Earth actually creates a measurable outcome on the moon. All right, so we've covered the scale of time. Let's switch gears to the scale of geometry. Because for these three beams to actually meet up on the moon, the aim has to be, well, it has to be almost perfect. We're talking about beams that are practically parallel, but not quite. Get a load of this number. That is the convergence angle. It's the tiny, tiny, tiny amount that the beams have to be tilted toward each other to meet up at the moon. If you were standing there watching them, they would look perfectly parallel, just shooting straight up. But over that vast distance, that minuscule angle is everything. To really wrap your head around that angle, check out this analogy. It's like three people trying to aim their laser pointers and hit the same exact quarter from 80 miles away. That's the level of precision we're talking about. It just shows you how wild this whole thing is. But here's the kicker. Even with that perfect aim, a laser beam doesn't just stay a perfect little dot forever. It spreads out over distance, and when your journey is to the moon, spreads out is a serious, serious understatement. This all comes down to a basic physics concept, beam divergence. It just means that every laser, no matter how tightly focused it is at the start, spreads out in a cone shape. So it starts as a point, maybe a few millimeters across on Earth, becomes something totally different by the time it gets where it's going. And by totally different, I mean this. The laser dot that actually hits the surface of the moon is 29 miles wide. Let that sink in. It's not a pinpoint of light, it's a gigantic circle of light, like a cosmic flashlight beam painting a huge section of the lunar landscape. And to put that in perspective, think about this. The beam of light that leaves this tiny little point in Los Angeles expands to cover an area that's almost as big as the entire LA basin it came from. It's like the light is painting a ghostly image of its own home on the surface of the moon. Wild. Okay, so hitting the target isn't just about aiming. It's also about timing. You can't just fire these things whenever you want. You have to wait for that one perfect moment, taking into account Earth's atmosphere and the moon's constantly changing orbit. Before the beam even gets out into space, it has to fight its way through our atmosphere. And the lower, denser, and frankly smoggier air down over Wilshire Boulevard scatters way more light particles, photons, than the thinner air up at Griffith or the Hollywood sign. So the Wilshire beam loses up to 22% of its power before it even leaves Earth. And of course, the distance to the moon is always changing because its orbit isn't a perfect circle, it's an oval. Sometimes it's farther away, and other times, what we call supermoons, it gets exceptionally close. The all-time record was actually way back in 1912, a record we won't even beat for a long time to come. So, all that brings us to this. When is the perfect time to fire? Well, the calculations point to one specific moment, what we're calling the golden minute. On this date, at this time, the moon is going to be at its closest point for the whole year and at its highest possible point in the sky over LA. That means it's the shortest possible trip through both space and the atmosphere. It's the cleanest shot you could ever hope for. Okay, this brings us to our final and maybe most mind-blowing scale. We're going from the cosmic all the way down to the quantum. We're going to actually try to count the particles of light making this incredible journey. So a normal 5-watt laser, right? It shoots out over 10 quintillion photons. That is a 10 with 18 zeros after it, every single second. It's not a beam, it's a flood, an absolute torrent of light particles blasting off the planet. And here is the final incredible paradox. Even with quintillions of photons starting the journey, by the time they spread out over that 29-mile-wide spot on the moon, the beam is 312 billion times dimmer than the sunlight hitting the surface right next to it. It's a whisper, a ghost of light in a sea of solar radiation. So think about the journey we just took, from a few miles on the ground in LA to nanoseconds to the width of a city, all the way down to individual photons. If a single simple beam of light from our own planet can contain such ridiculous, contradictory scales, it just makes you wonder what other secrets are waiting out there for us to find in the dark.